we need to show that this relation, that is row column operations, is an equivalence relation. For that, I need to show that this relation is reflexive, second symmetric, and third transitive. If they satisfy these three conditions, then we say that the given relation is an equivalence relation. First one is we need to show that the relation is reflexive, right? Let's take three matrices A, B and C, and let this be m by n matrices. That is, the number of rows are m and the number of columns are n. The matrices having the number of rows and columns to be m and n respectively. Now, since I can write the matrix A to be equal to, if I pre-multiply this matrix A with identity matrix of order m and post-multiply this matrix with identity matrix of order n, then I can get back this A. So from this we can say that therefore A is row column equivalent to A. So thus the relation is reflexive, right? Next, to show that the relation is symmetric, for that A is row column equivalent to B, and we need to show that B is row column equivalent to A, right? If A is row column equivalent to B, then what we are saying that B is obtained from A by applying some elementary row operations and column operations, right, in some order. So let's separate out the row operations and column operations, but keeping the respective order the same. And suppose that corresponding to pre-multiplication by the elementary row matrices, let's say E1, E2 up to so on ER in order, right? And by post multiplication by the elementary column matrices, let's say F1, F2 up to so on Fs, right? Thus, I can write this B to be equal to multiplying this A with the pre-elementary row matrices, that is the product of these matrices, and post multiplying the column matrices, the elementary column matrices, that is these one, the product. Because I need to show that A is obtained from B by applying the row column operations, so I need to make this A alone. And because these matrices are elementary matrices, so these are your invertible matrices, so their inverse exists. So now this A can be written as pre-multiplying the B with the inverse of the product of ER up to E3, E2, E1, and post-multiplying the inverse of the product of F1, F2 up to so on Fs. As EIs and FJs are invertible, right? Their inverse exists. So this is further equal to, just open the inverse, so you will get, because this is a product, so this will be E1 inverse multiplied with E2 inverse up to so on ER inverse. Please remember that you have to start with E1 when taking the inverse into B, and this is Fs inverse so on up to F2 inverse and F1 inverse. Very fine. So this implies what we are saying, that this B is obtained from A by applying the row column operations. Pre-multiplication of the elementary row matrices corresponds to the row operations. Post-multiplication of the elementary matrices corresponds to the column operations. Next is transitive. So for transitive, we need to take the two relations. Let A is row column equivalent to B and B is row column equivalent to C. Please remember, this is your matrix, okay? Don't confuse with this RC. Here C is the column operations and this C is your matrix. Now as B is obtained from A by applying the row column operations, so there exist elementary row matrices for this A. Let's say E1, E2, E3 up to ER. And elementary row matrices for B, let's say P1, P2 up to PL in order, right? And now writing the elementary column matrices for this B. So this is F1, F2, F3 up to Fs. And elementary row matrices for C. So this is Q1, Q2, Q3 up to QP. In order, right? Such that B is equal to, just pre-multiply the matrix A with the elementary row matrices, and you have to write the product starting from ER up to E2, E1. And post multiply the product of elementary matrices, that is these one, the column matrices. So you have to start with the product F1, F2 up to Fs. Similarly, because C is obtained from B by applying the row column operations, so C is equal to, yes, pre-multiply this B with the row matrices for B. So this is, just start from PL up to P2, P1, this product, and post multiply with the product of the column matrices, that is these one, and you have to start from Q1, Q2 up to QP. Now we need to get that A is row column equivalent to C, right? Okay, so we need to eliminate this B. For that, just put the value of B over here. So therefore, C is equal to, this is the product PL up to P2, P1. And now here, instead of B, I'm writing the value of B as this. So this is ER up to E2, E1. And this is A. And then this is F1, F2 up to Fs. And then this for the product. So C is equal to then PL up to P2, P1. And then the product ER up to E2, E1. Collecting all this product of the elementary row matrices, and this is A, and also collecting the product of the elementary column matrices. So this is Q1, Q2 up to QP. So we are getting C by pre-multiply or post-multiply the elementary matrices to this A. So this implies C is obtained from A by applying the row column operations, right? So thus the relation is transitive. So thus the relation is RC is transitive. And since the relation RC is reflexive, it is symmetric, and also transitive, therefore the relation RC is equivalence relation. Alright, thank you.